My name is Monika Rusiecka, and we need to talk about chlorine. But before I start, I wanted to, it's very special for me to be here because I did my PhD at McGill, and I wanted to first credit my PhD supervisor, Don Baker, who first introduced me to experiments, and John, who actually was on my thesis defense committee. So it's thanks to Don that I do, and John, that I do have a PhD after my name. And I also wanted to acknowledge Bernie Wood, who first took me on this volatile train. And I'm working with Bernie right now at Oxford. So, and I also wanted to acknowledge the First Nations, who are the traditional stewards of the lands on which we meet today, on which McGill stands. So we talked about experiments, and I wanted to start by talking some more about experiments. So doing a good experiment requires strict control of different parameters such as pressure, temperature, FO2, any other parameters that might be crucial. So before you start an experiment, you should ask yourself, what are you trying to accomplish? What are the potential reactions that are happening? So what do you need to control to say something about your system? You need to know what apparatus you are going to use and what is the best method to be used for the experiment. And there are a lot of problems, but if you, and limitations, but there are a lot of methods, so you can choose the right one. So long story short, I wanted to say that good experiments are hard, and a lot of the work happens before you get anywhere near a machine, because you have to think about what you're trying to accomplish. So now let's get to halogens. So starting broad, the halogen budget of Earth's main geochemical reservoirs. So as we can see here, the halogens are common in the terrestrial systems, but they're not very abundant. And this is just one example of the bulk silicate Earth abundances of different halogens. And we can see that for chlorine and bromine, they're mostly present in seawater and evaporates. For fluorine, the majority is blue, which means the majority is in the Earth's interior. And I thought this was interesting that most of iodine is in marine sediments, actually. Apparently, iodine is very, likes the organic molecules very much, but there might be some iodine in the Earth's core because iodine also likes metals. So now how halogens cycle the Earth. So we have the chlorine is the most abundant one. We have a lot of it on the Earth's surface, in seawater, evaporates. So what happens in subduction zones? We have the halogens going down in subduction zones. Some of it will be released early from pore fluids. Some of it will then be released a little bit further down during breakdown of halogen-bearing minerals, such as serpentine group minerals. And then we can have some of the halogens going into going up through the mantle wedge and the crust, and then we can have some melting induced by halogens, and then we have halogens going up to the surface through volcanoes. And now we'll focus on the top of this picture, which is the volcano. So we know that most important and the most abundant volcanic volatiles that received a lot of attention are water and CO2. So it's mostly water that is in those gases. sulfur species also received a lot of attention due to their abundance and sensitivity to redox conditions, but do not dismiss halogens because they can have a profound impact on the magmatic systems and the environment. So we have halogens dissolved in magma in this picture, and then we can have some of the halogens going into the hydrothermal system that Andrew was talking about. They often have a lot of chlorine and other stuff, but mostly chlorine. And then some of the halogens can go up and be released in volcanic emissions. And then some of it, as HCl and HF, HBr, etc., can be deposited on the surface of the Earth through wet deposition, which is through rain, or dry deposition on ash particles. And then some of it at the vent site and in the plume can undergo a series of reactions to create ozone destroying species such as BRO or CLO or stuff like that. So now let's focus a little bit more on chlorine and how chlorine is dissolved in the magma. So due to their higher ionic radii and negative charges, halogens are believed to replace oxygen in silicate melts. And we have here two reactions by which chlorine can potentially dissolve in the melt. So if the reaction A is correct, chlorine content in the melt should increase linearly with chlorine fugacity and decrease with square root of oxygen fugacity. And if reaction B is the one by which chlorine dissolves in the melt, chlorine content in the melt should increase linearly with square root of chlorine fugacity and decrease with fourth root of oxygen fugacity. And it has been shown by someone who's in this room, Richard, that in fact it's the reaction B that is how chlorine dissolves in the melt, and it varies. The chlorine content of the melt varies linearly with square root of chlorine fugacity and fourth root of oxygen fugacity. So now in this part, I will show some of my experiments on hydrous melts. So I did piston cylinder experiments using various compositions from basalt to rhyolite at 1300 Celsius at half, 1 and 1.6 GPa with various water contents, underwater, undersaturated conditions. And so here is the capsule design. So we have, we know from this equation by which chlorine dissolves in the melt that we need to control chlorine fugacity and oxygen fugacity to say something about chlorine content of the melt and how chlorine dissolves in the melt. So to control oxygen fugacity in this study, we used a graphite capsule with silver carbonate as source of CO2, and therefore we could control the oxygen fugacity at the CCO. So there was a question about the control of FO2 and kinetics. So this is a gas atmosphere and the gas is everywhere. So this is how you control the oxygen fugacity in this case. So we have the graphite capsule, the silver carbonate, and this is enclosed in a platinum capsule. And then on the outside, we have a hydrous glass, which is in gold palladium capsule, which limits the loss of water by decreasing the gradient of water contents between the outside and inside. So this is because platinum is permeable to hydrogen. So if you have very little water on the outside, you have a lot of water on the inside, you can lose water during the experiment. And additionally, we used a peroxide ring to additionally try to keep water inside. And then to control chlorine fugacity, we used a mixture of silver chloride and silver iodide, which is mixed in with the sample, which is in the graphite capsule. So what it looks like, because I realize that not everyone does experiments. So this is actually a picture not in a peroxide ring. This is just a capsule, platinum capsule inside the magnesium oxide ring. And then to put that sample into a piston cylinder, we have to have a source of heat. So we have a graphite heater, the furnace here. And during the experiments, current is applied to this, and that's how we generate high temperature. And then in piston cylinder, high pressure is generated using squeezing, mechanical pressure. It's just squeezing of the capsule. So this is the assembly. This is what the machine looks like. This one's name is Bertrand. It says there on he has a name tag. And this is what the assembly looks like in person. So this is not filled yet. There is a graphite heater on the inside, and then outside you have a sleeve. So this is calcium fluoride pressure medium. And then outside there is also a lead foil, which is just a lubricant inside the machine. So back to my experiments. During the experiment, the chlorine buffer decomposes and creates chlorine gas and metallic silver. And this is what it looks like after the experiment. So we have our melt, which is now glass in the middle. It's not the best picture, but it's glass in the middle, and outside it's graphite. So it's not like glass in the middle and then outside it's also glass. It's glass and graphite. Outside we have the metallic silver, and we have the leftover buffer, which means that our experiment was buffered during running, because not all of the buffer is spent. And so we learned already that this equation is how chlorine dissolves in the melt. For this reaction, we can define an equilibrium constant, but we don't really know activities of Cl- and O2- in the melt, but we can create an analog to this reaction constant, which really preserves this important relationship. I don't have a phone here. Oxygen fugacity and chlorine fugacity relationship. And this analog to a reaction constant is called capacity. So this is chloride capacity, preserves this relationship, and it depends on pressure, temperature, and composition. So how does the solution of chlorine depend on composition? So here we have an example of, we have chlorine on one axis, SiO2 on the other axis. We have fixed temperature, fixed pressure, fixed water content, fixed FO2, fixed chlorine fugacity. And these conditions, we can separate the effects of composition. So we have chlorine content at these conditions going down with increasing silica content. So we have slightly above 3 weight% chlorine dissolved in a basalt, but we have around half weight% of chlorine dissolved in a rhyolite. So now let's talk a little bit about water and the effects of water on how chlorine dissolves in the melt. So we have chlorine on the y-axis again, but this time we have water on the x-axis, and at fixed FO2 and chlorine fugacity, this is just one basaltic composition, so the composition is also fixed. At each pressure and temperature, chlorine content increases with increasing water content of the melt, but this is underwater, under saturated conditions. There is no aqueous fluid around, so that's important distinction. So now we talked about the analog to reaction constant, the chloride capacity. So because we controlled in the experiment the chlorine fugacity and oxygen fugacity, we know them. So this is those two things we know. We know chlorine content because we can measure it. And then we can calculate this chloride capacity for each of our experiments and the anhydrous experiments of Thomas and Wood. And then we can regress this chloride capacity against pressure, temperature, and composition of the melt. And this is the equation we end up with. So we have chloride capacity, their compositional terms, temperature, and pressure. And what is really interesting here is that even though I said that chlorine content increases with increasing water content, there is no specific water term in this equation, which means that water is acting as a diluent, diluting the major effects of other cations, because to calculate mole fractions, we have to have a sum of cations, and then we also have water that's diluting the other cations. So that's the explanation of how water affects the chloride capacity. So now, because we used water in our experiments, we can say something about the main chloride present in volcanic gases, which is HCl. And if we have these two reactions and we define reaction constants, we can say something about fugacity of HCl. So we have here the KHCl, and it's either the microphone or me showing stuff. So, but you can see there that there is our familiar ratio of square root of chlorine fugacity to a fourth root of oxygen fugacity. And because we defined chloride capacity, we can now replace this ratio with chlorine content and chloride capacity, which we can calculate from pressure, temperature, and composition. So for our hypothetical melt, we do not need to know specifically what was chlorine fugacity and oxygen fugacity to calculate HCl fugacity, which is very handy. But we do have to get an estimate of water fugacity, which we can get from water models, and the KH2O for the reaction, which we can get from thermochemical tables. And the KHCl we can also calculate from the available data from thermochemical tables. There have been, unlike for HCl, there have been a lot of experiments on chlorine-bearing aqueous fluids. So there are a lot of experiments where silicate melt was put in with chlorine-bearing aqueous fluid, and usually in this fluid we have dissolved NaCl or KCl, sometimes iron chlorides, sometimes some other chlorides. And then I said that experiments are hard. These experiments are extra hard because, as there was discussed here, measuring fluids is non-trivial, and usually it's done by mass balance, the composition of the fluid. And there's another issue with chlorine, because in order not to dissolve a lot of the major elements from our melt into the fluid, we have to use the very small volume of fluid. So that makes calculating mass balance really hard. But there's some general things that are universal, whether you use the chloride capacity approach or whether you put your melt in equilibrium with an NaCl bearing fluid. So we can see that one of the things that is showing here is that the compositional dependence is showing the same thing, because this is the DCl fluid melt. So the more silica rich your melt is, the more of it will be going into the fluid, not into the melt. But there is another thing, because of how we did our experiments. Now we can try to combine our experiments with the experiments that were done in this way. For now, for HCl. So this is some experiments from literature by Aleti et al., Samaro and Samon Erebus. And then we can take their compositions and all their parameters, pressure, temperature, which they controlled. They also had OFO2. And we can take an equation of state, such as modified Redlich-Kwong in this case, and calculate the composition of the fluid that would be in equilibrium with the melt, and we can calculate HCl in this fluid, which is valid at low pressure. I mean, at higher pressure, you would have to consider all the other chlorides. And we can play further and take natural melts. So this is a suite of melt inclusions. I took them from, I think, Georock, just because and then I had to search through papers, because I only wanted when the melt inclusions were the author's estimated pressure, temperature, and preferentially FO2, so I can say something about chlorine fugacity, because to calculate chlorine fugacity, we need to know oxygen fugacity. But if we do know all these things, we can calculate fugacity of chlorine in the gas that would be in equilibrium with our melt. And as you can see, the fugacity of chlorine in natural system is pathetic. It's 10 to the minus 10 to the 10 to the minus 6. It's very, very low. But if we look at HCl fugacity, the story is different. So we have the HCl fugacity between 10 to the minus 1 to 10 to 2, which is a lot higher. So it means that it shows why HCl is the main chlorine species in volcanic gases and not chlorine. And it also shows that you can't really dissolve, you can't really degas chlorine unless you have water present. Water is key for degassing of chlorine. You can also play a little bit more and calculate the composition of gas that would be in equilibrium with the melt, and depending on what models you use and what parameters you set, you will get a different answer. But in general, you can see here for sulfur and HCl. So the sulfur was calculated using Gorochovsky and Wood 2026 model for sulfur, and HCl was calculated using the equations that I have shown before. And you can see by comparing just this ratios in the melt and the ratios calculated in the gas, that the gas story says more about what was happening than just looking at the melt. And we can see the differences in degassing of chlorine and or HCl and sulfur. And then we can go a little bit even more further, because at the vent site and in the near vent plumes, the halogen species undergo the oxidative dissociation, forming halogen radicals, which can then be further oxidized to form other species, such as, in this case, ClO. And we can calculate from gas in equilibrium with a melt how much of these species we would produce. And we can see, I mean, whatever the numbers are, there's two important factors. So it depends on how much of the volcanic gas is mixed with air, because air is the source of oxygen. And also for the gas composition, it depends on how much water is in the gas, because water is also important for oxidation of these halogen species. So we saw that chlorine content increases with increasing water content of the mode. We saw that water is, however, it doesn't have a term in chloride capacity, which means that water is acting as a diluent, diluting the effects of other components. We can calculate fugacity of HCl and fugacity of chlorine in gas in equilibrium with a melt. And we learned an important lesson that water is key for chlorine degassing. And then there's some work in progress that I will be presenting in a poster that I'm now trying to get an expression for activity of NaCl, so we can try to calculate the speciation of chlorine in fluids. And I'm using a mixture of sodium chloride and sodium iodide, which is analogous to the sodium chloride and silver chloride, silver iodide. And we have some indications of the compositional effects, because we go from up there, the high chlorine content is a basalt, and we go down to rhyolites and phonolites. And then we have, I wanted to plug volatiles at Goldsmith, so I'm running a session on Friday. Terrible time. Friday afternoon. Please don't leave by then. And we have a keynote from Sarah, who's in the room, and we have an invited speaker, Lauren Gorchowski, who will talk about the sulfur at low temperatures, because it's not a straightforward story. I have a talk in a session that is dedicated to Bernie Wood for his 80th birthday, which is on Thursday afternoon and Friday morning. And I have a poster on Thursday afternoon. And yes, I'm doing too much at this conference. And so thank you. And if you want to read more about my work, you can read this paper. And then there is an upcoming paper from Lauren and other people about bromine in silicate melts, and something about HBr also is in this paper. So it will be in chemical geology. Thank you. Oh, and if someone asks a question, can you speak very loudly, because I have a little bit of a problem hearing.
We do have time for questions, and I think we should all congratulate the self-promotion too. I think. So, questions.
I mean, I really overdone it at this conference, so I have to.
No, I don't think you oversold it. Yeah. Anyone?
I mean, we can also, I think people want coffee and pastries.
No, but the energy's dropping, but that's okay. But sort of a diffusion problem. Anyone? Okay, so we'll go with Shay. Yeah.
What do you think's needed to bring chlorine into the fold for modeling? You know, now we can do hydrogen, carbon, sulfur together. What's needed to bring the work you guys are doing on chlorine, you and others, into that sphere?
I mean, you can already put in HCl and chlorine gas, because there are expressions for that, as I shown. But you have to be careful, because for chlorine is fine. For HCl, assuming that all chlorine is HCl at pressures higher than, like, depending on composition, 50 MPa, 100 MPa, that's a little bit of a stretch. But then if you can get an expression for NaCl activity, and you can combine both, and you can have equations where NaCl and HCl are together, and you can do similar things as people have done for sulfur, just for in different contexts. Then I think you can include them, but HCl and chlorine you can include.
Eddie?
Oh, sorry, I didn't.
That was amazing, very difficult experiments, and it's so good you thinking about them before you run them, because you must have had to think a lot. Did you notice any sodium stripping from your melt into the fluid?
Sorry.
Like, did you lose sodium during your
I think you have to switch off. So yeah, I mean, it's only because I think people online can only hear with. So yes, there is some sodium stripping, but you can calculate, and I did this, and I mentioned that in my paper, because there was a little bit of sodium loss, but you can recalculate how much this gained sodium in a buffer would change the buffer composition, and it's basically it's like 1% change, so it's no change at all. And then
actually, I hadn't thought about it messing up your buffer, but that's a really good point. The reason I was asking is it didn't turn up in your equation for what?
Oh yeah. Oh, this sodium. Yeah, so there was no sodium term in the equation. It just didn't, during the regression, it didn't show up as a significant component. It does show up, obviously, when I don't have enough experiments for NaCl yet, but I did like preliminary regression that was crap, but it did show some of the components that would potentially be important, and obviously it's sodium, it's also iron and magnesium, and I have that on my poster. And
See you at your poster.
Yeah, I wanted to say that yes, these are amazing experiments, but these techniques have been around for a really long time, and this particular buffering of chlorine is from 1973 from France and Oyster. And I wanted to mention this because I've heard some people dismiss experiments from 80s or 70s because, they didn't propagate errors, or the analysis were not that good yet. But people in 70s and 80s really thought what they were doing. So they were really good experiments. So don't dismiss something just because it's old.
That's a good lesson for all of us.